All right, so we're doing section 1-2, properties of real numbers in Advanced Algebra 2 today. Our learning objective is to graph and order real numbers and to identify properties of real numbers. Our essential understanding is the set of real numbers has several special subsets related in particular ways. So we need to decide how all these items, if at all, they're related to each other when speaking of numbers. Okay, so to recap, and this diagram should be in your notes with it labeled correctly. Natural numbers are counting numbers starting at 1 and counting up forever and ever, amen. Whole numbers are counting numbers starting at 0 and counting up forever and ever. Integers are whole numbers and their opposites, including zeros. Sorry, integers are fractions. No, whole numbers and their opposites, including 0. It's got to be whole. -1, +1. Both of them are integers. Integers are positive and negative whole numbers, including 0. Rational numbers are fractions created from integers. If you can make a decimal into a fraction of integers, it is also rational. Irrational numbers are non-repeating, non-terminating decimals, usually created by square roots, or pi is a famous irrational number. And then real numbers are all the numbers in the universe except for imaginary ones, which happen when you take the square root of a negative number. All right, so in your notes, write these instructions down. Classify each variable according to the set of numbers that best describes its value. So we have 3 different items here. We have the number of times n a ball bounces. Classify each variable according to the set of numbers and best describes value. And the height h from which the ball drops. That's our first item. So go ahead and I'll give you a second to write that down. All right, so the number of times n a ball bounces. Can that be a natural number? Does the numbers 1, 2, 3, 4, do those numbers make sense for a ball bouncing? The number of times a ball bounces, yes. So let's move that up to whole numbers. Whole numbers are 0. Is it possible that our ball bounces 0 times? Yeah, because before I start the experiment, we're at 0. So whole numbers also make sense to this problem. Integers. Does it make sense that a ball bounces positive or negative whole number times? No, you can't bounce a ball -5 times. So we get stuck right here at whole. So let's put whole numbers. The height from which the ball is dropped. Can the ball be 1 foot from the ground? Can the ball be 2 feet off the ground? Can the ball be 3 feet? Yeah, so all the natural numbers apply to our ball height. What about whole numbers? Can the ball be a height of 0? What scenario is our ball a height of 0? Right?
It's being dropped, so no.
So how high off the ground is my pen that I just dropped on the ground? 0. So 0 indicates the ball is on the ground. So we can be 0. So whole numbers work too. Integers. Can my ball height be positive or negative whole number?
What if it goes under?
It can if you say, if I'm here at 0 and I have a space, a crater that is below ground level, then it would be a negative height. So your height depends upon where you set is negative, or where you set your 0. So it is possible. Or if I drop it off of a cliff, where I'm standing is 0, I drop it off the cliff, we now go. Or think about water. My water level is 0, and I throw it, and it goes in the water, then under the water. Underwater would be negative. So it's plausible to have integers here. Is there any reason that my height has to be a whole number? Could it be like 2.5? Could it be 2.61784? Yeah. So we not only get to be an integer, but we also get to be rational. And is it a possibility that my height could be irrational? Ian, what do you think?
Oh, I was gonna say about the ball bouncing and it could be a rational number, but it can't be an integer.
Can we say that the height is going to be all real numbers? Because we know it can be negative, it can be a decimal, it can be a fraction, can it have pi in it? Yeah, all those things are okay. So we're going to say that the height is real. All right, so then let's look at the next one, the year Y and the median selling price P for a house that year. So can a year has to be a whole number. I guess technically you can be a half of a year, but it's 2016 right now, and it's going to be 2016 until it's 2017, right? So we're just going to say that we are a whole number. And then the median selling price, well, we definitely know, yes, I'm just gonna, I guess technically you can pay somebody to take your house off of your hands, but usually you don't do that. You just, the minimum you can sell your house for is 0, and then the maximum is whatever anybody's willing to pay for it. Are there any restrictions on whole numbers, or does it fractions, or anything in between? Price?
I actually have a question.
Okay, wait. Okay, so I would say the selling price would have to be because we have to stop at the penny, right? Because you can't, I don't know. Do we stop at the penny? What do you guys think? So we're going to say, I'm going to say rational. The circumference of a circle, C, found by using the formula C equals 2 pi r. C is always going to have pi in it. Pi is irrational unless it's divided. Unless r is something over pi, and then it's rational. I'm going to say real on the circumference. Okay, so in your notes, I want you to graph each number on a number line. Make sure you have a number line on your paper. And look how amazing I am at writing synchronous intervals. They're all the same. But try to get your intervals all equally situated. Let's put 0 in the middle. -1, -2, -3, -4, -5. I'm sorry, this is +5. This is -5. Here we go. Okay, we're going to place each of these numbers on the number line. All right, so on our number line, -24 is a little bit larger than -5. -4 2/3 is a little bit past halfway between -4 and -5. -2 1/5 is really close to that -2 mark. -2 is on -2. -1.4 is a little, you guys are really good, really precise in your placement. Negative 1.4 is a little bit to the right of negative, halfway between negative 2 and negative 1. 0 is on 0. 2.5 is halfway between 2 and 3. 3.5 is halfway between 3 and 4. Square root of 10 is a little bit more than 3. And 4.8 is a little bit to the left of 5. Easy peasy. All right, so we're going to compare these numbers using greater than or less than. So I think this case. Okay, to recap, 16 is greater than square root of 16. Negative square root of 3 is greater than negative square root of 5. 4 is greater than square root of 12. And 4.7 is less than root 26. Alright, so let's go over these topics real quick. Our essential understanding is that properties of real numbers are relationships that are true for all real numbers except for crazy 0. We are going to be talking about opposites. That is an additive inverse. Any number A, for any number A, it is negative A. So if you're looking for an additive inverse, you just change the sign of what you're originally starting with. So a number plus its additive inverse is always equal to 0. So you can ask yourself, what do I add to this number to equal 0? If it's a positive number, it would be a negative value. If it were a negative number, it would be a positive value. A reciprocal is a multiplicative inverse. For any number A, the reciprocal is, and I didn't write this down because I didn't want to worry about fractions, 1 over A. When you multiply a number by its reciprocal, you get 1. When you add a number to its additive inverse or its opposite, you get 0. When you multiply it by its reciprocal, you get 1, 0, or 1. If you have a fraction to begin with, the reciprocal is whatever the flip of that value is. So that brings us up to our properties. We use these properties all the time to solve equations. So that's what this is building to, be able to solve equations. If you vary from the properties of real numbers for solving equations or the math rules, then you don't get the right answer because you're not solving the equation correctly. So that's why we go through all this. So we're going to let A, B, and C is real numbers. Closure is if A plus B is a real number and A times B is a real number. I frankly don't ever use that terminology, so whatever. Commutative. The way I remember commutative is because I took history and I learned about communism. And communism says that everybody is equal. It doesn't matter who's first or who's last. We're all going to wait in this red line together. So A plus B is equal to B plus A. So if that works for addition, and same with multiplication. You can switch the order. Everybody's all on equal playing field. It doesn't matter who's first or second. Associative is really similar to commutative. I get those two mixed up all the time, but it's like this. These are my associates. Sometimes I'm going to be working with this associate. Sometimes I'm going to be working with that associate. At the end of the day, we're all going to be the same associate. So it's like this. I can group A and B together, or I can group B and C together. In this scenario, I can multiply A and B together first, or I can multiply B and C together. Associative. Identity is for addition is when you add 0. For multiplication, it's when you multiply by 1. It's whatever value gets you out your original value. So that's how I remember it. Inverse, we just talked about those two things. It's either the opposite if you're talking about additive, or it's a reciprocal if you're talking about multiplication. Distributive property, it's if anything on the outside of the parentheses gets distributed to everything on the inside. So A times B plus C is equal to AB plus AC. All right, we're going to take a moment. We're going to write. You guys have all this information already. I printed it out, taped it there. So you're going to write each of these.
Wait, that's
It's not? Okay.